Assalamu alaikum. Let's begin lecture number 8 of CS218 Data Structures and Algorithms. In the last lecture, we looked at the similarities and differences between arrays and lists. We learned to implement one-dimensional arrays. We were introduced to the linear search algorithm for arrays. And we found time complexities for all our implementations. The topic of this lecture is arrays and lists. We use chapter 2 of book 1 for this topic. Today I present to you the binary search algorithm. This is the second search algorithm that you can use on arrays. But there is a limitation. This algorithm only works on sorted arrays. The algorithm that I present here runs on arrays that are sorted in ascending order. That is, lower values are at the start and higher values are at the end. You can see that I have imported the file containing the array class. The bin search function takes two arguments, the array and the item that you are looking for in the array. First, we initialize two variables. Low is assigned 0 and high is assigned n minus 1, where n is the size of the array. A while loop runs as long as low is less than equal to high. Inside the while loop, we set mid to be equal to high plus low whole divided by 2, and this is an implementation of the floor function. So if the answer is 7.5, mid will become 7 and the 0.5 will be taken off. Then we compare the value at the mid of the array to item, and if this comparison is true, we return mid. Otherwise, we again compare if item is less than array mid. In that case, we set high equal to mid minus 1. If this is also false, we set low equal to mid plus 1. When we come out of the while loop, we return none. You will find it difficult to understand the code as it is, so I present to you an example. Look at my array. Can you see that the array is sorted? I want to find 20. So when the function starts, it sets low and high. Low is set to 0, high is set to 7. Low is less than or equal to high, so we enter the while and we set mid. 0 plus 7 is 7 divided by 2. The answer is 3.5. Mid becomes 3. Now we compare the element at mid with 20 and we say that 20 is greater than 10. So the first condition is false. Then the condition for the elif is false. So we come to the else and we set low equal to mid plus 1. What has just happened? We realized that the item we are looking for is greater than the item at mid. So this means that the item we are looking for must be on the right side of mid. So now our focus has shifted to elements on the right side of mid. Again, when we check the while condition, low is less than or equal to high. So we move into the while and set mid. 4 plus 7 is 11 divided by 2, 5.5. Mid comes out to be 5. Now we compare the mid value with 20. 20 is greater than 17. The if condition is false. The elif condition is false. So you set low equal to mid plus 1. What happened this time? We realized that 20 is greater than 17. So 20 must be on the right of 17. So now we have restricted our focus to the elements on the right of 17. Again we see that low is less than or equal to high. So we move into the while loop and we set mid. 6 plus 7 is 13, divide by 2. You get 6.5, mid is 6. Now I compare the mid value with the item and the if condition is true. So I return mid. This is a successful search. Have a look at another example. Here is the array. I have to find 15. I set low equal to 0 and high equal to 7. Low is less than equal to high. So I calculate mid. 0 plus 7 is 7 divided by 2. The answer is 3.5. Mid is at 3. I compare 15 with the element at mid, which is 10. 15 is greater than 10. The if condition is false. The elif is false. So the else executes. Low is mid plus 1. So here we are. We realized that 15 was greater than 10. So we shifted our focus to elements to the right of 10. Low is less than equal to high. So we enter the while loop again and calculate mid. 4 plus 7 is 11. 11 divided by 2 is 5.5. Mid is 5. We compare 15 with 17 and realize that 15 is less than 17. The if condition is false, but the elif condition is true. So high will go to mid minus 1 and we have this. Low and high both are at 4. We realize that 15 is less than 17, so we shifted our focus to elements to the left of 17. Now within our focus there is only one element. Low is less than equal to high. Mid will also come and point at 4. And we compare 15 with 13 and realize that 15 is greater than 13. The if condition is false. The elif is false. The else executes and low becomes mid plus 1. Now you can see that low is not less than equal to high. So we cannot enter the while again. We come to the last line of code and return none. We now look at the complexity of binary search. The algorithm has a best case and a worst case. Let's talk about them separately. The best case occurs when the item is present at the index calculated as mid in the first iteration. Take an example. This is an array. I want to find 10. I set low equal to 0, high equal to 7. Low is less than equal to high. I calculate the mid, which comes out to be 3. I compare the element at mid with 10. 10 is equal to 10. I found it and I return 3. The number of iterations of the while are 1. So the best case is O1. Continuing with time complexity of binary search, the worst case occurs when the item is present at the first or the last index. The item is not present and the search takes us to either the first or the last index. Let us take an example. This is our array and we want to look for 25. I set low to 0, high to 7. Low is less than or equal to high. I compute mid, which turns out to be 3. I compare 25 with 10. 25 is greater than 10. So I shift my focus towards the right of 10. Low is mid plus 1. This happens. Low is 4, high is 7. Low is less than equal to high. I calculate mid, which comes out to be 5. I compare the mid value with the item. 25 is greater than 17. So I shift my focus to the right of 70 and this happens. Low is mid plus 1. Now low is 6, high is 7. And since low is less than equal to high, I compute mid, which comes out to be 6. I compare 25 and 20. 25 is greater than 20, so I shift my focus to the right of 20. And this happens. High and low are at the same place. Low is less than equal to high. I calculate mid, which comes out to be at 7 too. I compare 21 and 25. 25 is greater than 21. So I will move the focus towards the right of 21. Low will be mid plus 1. But there is no array beyond index number 7. So what happens is low becomes greater than high. Now we cannot move into the while. And we say that we cannot find 25 in this array. So what is the time complexity of binary search in the worst case? Let the total number of iterations of the while loop be r. In the first iterations, we are searching through n elements. I can write n as n upon 2 to the power 0. But in the next iteration, we are only working with half of the elements, either on the right of mid or on the left of mid. So this means that in iteration number 2, we are working with n divided by 2 to the power 1. In the next iteration, again these elements will be halved. So in iteration number 3, we are searching through n upon 2 to the power 2 elements. This continues. In the last iteration, which is the rth iteration, we are searching through n divided by 2 raised to the power r minus 1. But in the last iteration, we are searching through just one element. So this means that n upon 2 to the power r minus 1 is 1, which gives us this equation. Applying log base 2 on both sides, you get r minus 1 is log of n. And from here, you can say r is log of n plus 1. What was r? R was the number of iterations of the while loop. So since we execute r iterations in the worst case, the time of the while loop or the time of the binary search algorithm is equal to r or log of n plus 1. From here we can deduce that the worst case complexity of the binary search is O log n. Concluding remarks on binary search. Binary search is a very fast searching algorithm as it has logarithmic rate of growth in the worst case. Binary search can only be implemented on sorted arrays. The first homework for you is this. You are given an array A. Apply binary search to find these items in A. First do it for 11, then run the algorithm for 43, and finally for 24. Count the number of iterations in each case. Sorting in an array. There are many algorithms that we may employ to sort a one-dimensional array. The first sorting algorithm that we will discuss over the course of this semester is the bubble sort. An array is input to the algorithm. The algorithm returns the array with elements in ascending order. A single element is pre-sorted. Please remember this. This line means that if you have a data structure in which there is only one element, then we can say that the data structure is sorted. Anything that has just one element does not need sorting. It is already sorted. Let us look at the bubble sort algorithm. Notice that I have imported the array class for this algorithm. The bubble sort algorithm takes the array that we want to sort and finds the length of the array, assigns this value to n. The outer for runs from 0 to n minus 2. The inner for runs from 0 to n minus 1 minus I, where I is the counter of the outer for. We do a comparison in which we see if array j is greater than array j plus 1. If it is, we swap the two elements. We assign array j to tmp, then we assign array j plus 1 to array j, and then we assign tmp to array j plus 1. To elaborate this algorithm, I present an example. This is my array. When I start, I is 0. Then I move into the inner for and j is 0. Now the body of the two fors compares 10 and 51. Since 10 is less than 51, nothing needs to be done. They do not need to be swapped. Next, j goes to 1. Now we compare 51 and 2. 51 is greater than 2, so the two elements need to be swapped. Then j goes to 2. 51 and 18 are compared. Since 51 is greater than 18, the elements are swapped. We have come to the end of the first pass, that is all the iterations for the value of I equal to 0. At the end of the first pass, the largest element, 51, has bubbled to its correct position. We start the second pass. I is equal to 1. The inner for loop starts. J is equal to 0. We compare 10 and 2. 10 is greater than 2, so they need to be swapped. And after swapping them, we go for j equals to 1. 10 and 18 are compared. No swapping required. We come to the end of the second pass. At the end of the second pass, the second largest element has bubbled to its correct position. We start the third pass. J is set to 0. We compare 2 and 10. No swapping is required. The third pass culminates and the third largest element has bubbled to its correct position. Note that in the remaining unsorted array, there is only one element. I told you that a single element is always pre-sorted. So we do not require another pass to say that the array is sorted. Let us see how bubble sort occurs when our array is already sorted in ascending order. Consider this example. You can see that the array is already sorted. Let us begin the first pass for I equal to 0. J equals 0. We compare 10 and 12. No swap is required. J equals 1. We compare 12 and 35. No swap is required. J equals 2. We compare 35 and 42. No swap is required. 42 has bubbled to its correct position. We start the second pass. I equals 1. J equals 0. We compare 10 and 12. No swap required. J equals 1. No swap is required for 12 and 35. 35 is in its correct position. We start the third pass. I equals 2. J equals 0. No swap required. End of the third pass. 12 is at its correct position. Since there is only one unsorted element remaining, we can say that the array is already sorted. You can see that the algorithm has no idea that the array it has been given is already in ascending order. Now that you have seen how the bubble sort algorithm behaves when the array is sorted in ascending order, I want you to run the bubble sort algorithm on an array that is sorted in descending order. That is, the higher values are at the start and the lower values are at the end. Time complexity of bubble sort. The comparison takes place in every iteration. Best case occurs when the comparison is false every time. This happens when the array is sorted in ascending order or the array has the same element at all indexes. Worst case occurs when the comparison is true every time. This happens when the array is sorted in descending order. Time complexity of the best case of bubble sort. In the best case, the comparison is false in every iteration. Assume the comparison is made in C units of time. When I equals 0, valid values of j go from 0 to n minus 2. Number of iterations is n minus 1. In each iteration, we do the comparison but never slip into the body of the if. When I equals 1, valid values of j go from 0 to n minus 3 and number of iterations is n minus 2. The last value of I is n minus 2. When I is n minus 2, valid values of j is 0 only. So the number of iterations is 1. Total iterations are n minus 1 in the first pass plus n minus 2 in the second pass, continuing to 1 in the last pass. So this was the equation for the total number of iterations. We can reorder it and write it this way too, since addition is commutative. Total iterations are n minus 1 divided by 2, 1 plus n minus 1. This is the formula for summation of an arithmetic series. Total number of elements is n minus 1. The first element is 1, the last element is n minus 1. So total iterations are n times n minus 1 whole divided by 2. The running time is the time spent on the comparison C multiplied with the total number of iterations. So Tn is C times n square upon 2 minus n upon 2. And from here I can say that the best case of the bubble sort algorithm is O n squared. Now let us look at time complexity of the bubble sort when the worst case happens. The comparison is true in every iteration. So the comparison is also made and the body is also executed. Assume that the comparison and its body is executed in k units of time. When I equals 0, valid values of j go from 0 to n minus 2. Number of iterations is n minus 1. When I equals 1, valid values of j go from 0 to n minus 3. Number of iterations is n minus 2. The last value of I is n minus 2. When I equals n minus 2, valid value of j is 0 only and the number of iterations is 1. Total iterations is the number of iterations in the first pass, n minus 1, plus the number of iterations in the second pass, n minus 2, continuing to the number of iterations in the last pass, which is 1. So this is the equation that we get for total number of iterations in the worst case. As before, this equation simplifies to total iterations is n times n minus 1 whole divided by 2. The running time is the time spent on the comparison and its body k multiplied with the total number of iterations. So Tn is k times n squared divided by 2 minus n divided by 2. And from here we can deduce that the worst case of bubble sort is O n squared, which was the same in the best case of bubble sort. So what are our concluding remarks on bubble sort? Bubble sort behaves the same way for both best case and worst case. If an array is already sorted, the algorithm cannot sense this condition and hence does not improve performance. Bubble sort is a dumb sorting algorithm. A smart algorithm would not sort if data is pre-sorted. Your homework is to change the bubble sort algorithm that you saw in the previous slides such that it does not continue looping after an iteration of the outer for in which no swap occurs. So I want you to make it smart. So what did we learn today? We were introduced to the binary search algorithm for arrays. We performed bubble sorting in arrays, and we found time complexities of all our implementations. At the end of this lecture, I remind you of the things that you have to do. You have to read the book, you have to do the homeworks. Even if you don't submit them, you still have to do them. You have to note your questions and put them up in the relevant online session. And if you have any suggestions, you need to email them to me. Take care and Allah Hafiz.